Hey everyone, and welcome. So today we're going to take a look at one of the most famous ideas in all of math, the Pythagorean theorem. But we're going to do it in a totally new way. We're going to forget the formula you memorized in school and see how this amazing concept can be unlocked for kids as something you can actually play with. Let's jump in. Yes, this one. We all know it, right? A squared plus b squared equals c squared. It's practically burned into our brains from middle school. It's the go-to, the one-and-done formula for any right triangle. But here's a crazy thought. What if starting with this formula is actually starting at the end of the story? And that, right there, is the big question for this whole explainer. It flips the script on how we usually teach math. What if all those symbols, the A's, the B's, the C's, what if they're the very last piece of the puzzle you learn, instead of the first thing you're told to memorize? So how in the world do you do that? Well, it all starts with a really powerful idea called an intellectually honest approach to teaching. And get this is not some new trendy idea. This comes from the legendary educator Jerome Bruner, way back in 1960. The key thing here isn't dumbing down the idea, not at all. It's about finding the true, beautiful core of a concept and presenting it in a way a child can genuinely grasp. So what does that actually mean? It means you take these big, floaty, abstract ideas and you anchor them in things a kid can actually touch, see, and mess around with. You go from the abstract to the real, building up a real gut-level intuition for how things work long before you ever introduce a formal equation. This image really says it all. The teacher's job is to be that bridge. They connect the world a child already understands, the world of play, of blocks, of curiosity, to the more formal world of big mathematical ideas. It's about making sure that what they learn today is a rock-solid foundation for whatever comes next. Okay, so let's see what this looks like in practice. For a kindergartner, maybe a first grader, the journey doesn't start with triangles or formulas. Nope, it starts with the most basic thing you can do in math, just counting. Check this out. On the left, you just have some red and blue squares. It's a counting game, simple as that. But then you just move them around a little bit, and on the right, whoa, something totally new appears. Those exact same squares are now hugging the edges of a right triangle, and this deep, important relationship in geometry just starts to emerge, all from counting squares. And the questions you'd ask a kid at this stage are just wonderfully simple. How many red ones are there? Which pile is bigger? Hey, what's that shape in the middle? You're not talking about area or hypotenuses, not yet. You're just planting these little visual seeds of a much bigger idea, all while they practice the basics. Okay, now let's jump ahead a couple years. Second, maybe third grade, this is where things get really fun. This is where a kid can have that amazing aha moment by actually holding a proof in their hands. So here's a classic way to show the theorem. You can see how the two smaller squares get chopped up and rearranged to perfectly fill the big one. It's proof you can see with your own eyes. It's super compelling, but what if we could take it one step further? I mean, seeing it on a screen is one thing. But what if you could actually pick it up? What if this big mathematical theorem became a game? And that is exactly what some designers created. On the left, you've got the computer model, and on the right, the real 3D printed puzzle. It's this incredible little hinged toy that physically is the Pythagorean theorem. It's not a diagram anymore. It's something you can play with. So when you pop the puzzle pieces out of the two smaller squares, they fit perfectly into the frame of the big one. There's no room to spare. A kid doesn't need a formula to know it's true. They've just proved it themselves. You just can't forget an experience like that. Okay, so we've counted blocks, we've played with puzzles. That's all great, but what's the real payoff? Well, now we get to see the serious consequences, as they say. We're going to apply this to a real problem you might see in 4th or 5th grade. So here's the setup. You've got 3 friends, Anna, Bill, and Carla. We know it's 6 miles from Anna to Bill and 8 miles from Anna to Carla. The big question is, what's the direct distance from Bill to Carla? This is the classic problem of finding the hypotenuse. Now, the traditional way is to just pull out that formula and plug in the numbers. But a student who learned through play, they can do something way more intuitive. They can literally picture the squares on each side of that triangle, connecting this problem all the way back to that first day of just counting blocks. Let's just walk through the logic. The square on the Anna to Bill side, its area is 6 times 6, so 36. The one on the Anna to Carla side is 8 times 8, so 64. And because of everything they learned with those puzzles, they know the area of the big square has to be the other two added together. 36 plus 64 is 100. So if the big square has an area of 100, what does its side have to be? 10. The distance is 10 miles. No formula needed, just understanding. So what's the big idea here? What's the point of all this? Well, this isn't just a cute teaching trick. This is about literally building better, stronger mathematical brains. Neuroscientist Dr. Laura Boyd puts it perfectly. She says that the very act of struggling with something, like figuring out that puzzle, physically changes your brain. That playful struggle isn't wasting time. It's the actual work that builds new connections and a deeper ability to learn. And here is the perfect analogy for all of this. Teaching these big ideas in a playful, intuitive way early on is like pouring the deep, concrete foundation for a massive skyscraper. You aren't building the 80th floor yet, but you're creating a base that's so strong it can support all kinds of complex, amazing structures later on. And that really just leaves us with one final thought. This whole journey was about seeing Pythagoras not as a dry formula, but as an entire world you can explore. And it kind of makes you wonder, what other big ideas in science, in art, in everything are just sitting there waiting for us to unlock them, if only we give ourselves permission to play first.